Okay, thank you everyone for the introduction. It's been really good to be back in Australia. It's nearly 10 years since I was last here. And when I was last here, I said, well, next time I come, I'm going to come for at least a month because of the jet lag. And I've come for 6 days. And it's been really good talking to people and the enthusiasm that people ask me questions about stuff. And so it's really good and I'm learning lots. And people are asking, saying, well, how's your jet lag? And it's doing really good. Paul said before this, he said, you know, you've probably given this presentation enough times that you can do it in your sleep. Well, I'm going to put that to the test, I think. So the work has been done by my colleagues, all my colleagues at the University of Bath. And the reason for the logo and the format of the slide is it was done under a European funded project called EcoC. This was what we call a Framework 7 funded project, which ran for 4 years, funded by the European Commission. And we had 18 partners across Europe, and it finished at the end of August. And it was, clay materials were very much a strong part of it. I still hope after the stupidity of Brexit that we'll still be able to involve in European projects, but we'll have to wait and see. In Northern Europe, I don't know if that's true in Australia, but in Northern Europe, they reckon we spend 80 to 90% of our lives indoors. And so clearly living indoors, eating indoors, sleeping indoors, working indoors, studying indoors, etc., the environment we create indoors has a huge impact on our health and in particular our well-being. So, and the basis and the background to this project is that studies have suggested that the quality of the environment indoors is actually getting worse, not better, in some buildings. So measures of indoor pollutant levels are often higher than outdoor levels. And there's been a lot of stories about diesel engines and problems with emissions in cities, but in some cases, the indoor air pollution is worse. And it's been ranked, and it's well known amongst health agencies and governments, that it's a big environmental risk to public health, the quality of the spaces we create here. Some studies suggest that 30% of new and remodeled houses have issues with indoor air quality, and in particular in relation to the move to increasing, and we've heard conversations about this already, about making our buildings more and more airtight. And as a result of making them more and more airtight, we are potentially leading to problems with indoor environmental quality. So there's a slight difference. I mean, indoor air quality is the quality of the air that we breathe, and indoor environmental quality is much broader. It includes issues of thermal comfort, acoustics, and more holistically. So this is the scenario. So this is a sort of traditional old house in, say, in the UK. So not particularly airtight. So you get cool air coming in and not very well insulated, so we're losing the warm air that we've created, and outside pollutants can also come into the building. But the scenario is, of course, now we're insulating the old buildings and, of course, our new buildings, so we're creating highly insulated envelopes, which is great for thermal energy efficiency, but we're also making them more airtight as well, so we're trapping some of that air in there. Now, passive buildings rely on mechanical ventilation, and when that mechanical ventilation, I think, works, then it, I think, keeps the air quality at a satisfactory level. But if it's not maintained properly, and of course the people operating them who live in these buildings don't actually know how to use them satisfactorily, then we get problems with build-up of moisture and humidity levels, of mold growth, of volatile organic compounds, off-gassing from the products and things and carpets and plastics we bring into our living spaces, and we generate particulate matter, and the moisture comes from us, from breathing, from our plants, from cooking, washing, etc. And studies show that, you know, we well know that with VOCs, for example, and low levels of CO2 that are, and also with jet lag, that our cognitive abilities diminish, or indeed when we get low levels our cognitive abilities improve. In the UK, then it's estimated, and I'm not sure where this figure came from, this is one of my colleagues, that it costs us £30 billion due to unproductive staff. The cost of an organisation is about, I think the breakdown is like an organisation might spend, say, 1% on its energy, 10% on sort of rent and buildings, and about 85% of its costs on its staff. So you want to make your staff as efficiently as possible, as productive as possible. And the National Health Service also recognised the health effects of indoor air pollutants as well, and it's also linked to things such as asthma, where we have really chronic high levels of asthma in the UK as well. And more broadly, then maybe up to 1 in 8 deaths globally are due to air pollution. Many of those, of course, due to indoor fires for cooking and heating. So the EcoSea project, its aim was to improve indoor environmental quality, reducing the reliance on active measures, ventilation, through using eco-materials or natural building materials, because we've long known that hygrothermal building materials help to regulate the humidity in buildings. So our objectives were to reduce embodied energy, improve durability, and aim to reduce build costs using natural building materials like, as shown here, with Claytex clay plasters, and utilising the benefits that we know about broadly called eco-materials or natural building materials in terms of their low energy, low carbon, have good life cycle impact, have good insulation properties, have hygrothermal, and are also vapor permeable as well. So in this case, overall, the project looked at a number of different products. So particularly this is about talking about our clay plasters, but also we looked at bio-based insulation. We looked at photocatalytic panels for indoor use, wood panel products with low VOCs. So often we bring in the wood panel products and they're the source of formaldehydes and other VOCs. And associated with this, design tools to help people use these products efficiently. So in terms of, well, if you design a space, how much clay plaster do you need in a given volume for it to be effective as well? So there's that aspect, which I'm not going to particularly talk about now, and then also developing wall panels, prefabricated wall panels. I guess many of you are familiar with this diagram or a version of it, which just shows the influence of humidity on different agents that affect our health. So the bottom scale here is 0 to 100% relative humidity. And then we've got different agents here, bacteria, viruses, fungi, mites, respiratory infections, etc. And then the height of these triangular bars is the intensity or the level of activity related to the humidity. So very low humidities, then bacteria and some viruses like very dry environments, and similarly some bacteria and viruses like very damp environments. But overall, there's this sort of optimal zone between about 40 and 60%, where most of these are at their minimum. And so if we can create this environment internally passively rather than through active ventilation, then hopefully we can create a healthier building for us to live in. So just to reiterate, in terms of trying to get the relative humidity between 40 and 60, in terms of controlling CO2 levels, that, naturally before we start breathing, then they're 350. I should imagine in this room, it might be starting to get to somewhere like 1,000 parts per million, where we might start to feel a little drowsy. Trying to control particulate matter, and in particular trying to control the amount of VOCs in the atmosphere as well, in parts per billion. There's been talk about hygrothermal wall performance, and this diagram attempts to sort of illustrate simply the sort of cycle between day and night. So in daytime, if this represents the wall, then with the solar radiation impinging upon the wall, then we see the temperature on that surface increase, the temperature profile increasing on that surface, and the humidity profile decreasing as humidity, as it dries, and the humidity passes through the wall. And we start to, as said here, charging the wall's heat reservoir or the thermal mass here, but it's not just the temperature, but also the effect on the humidity. Then at night time, as this side cools down, then the humidity goes back up and the temperature drops off as we that heat is retransferred back into the space on this side of the panel, and part of that swing of using thermal mass, but not just the thermal mass, the latent heat energy effect of the humidity as well. And I was trying to think of an example to illustrate that in experiment. So this panel here is actually a hemp lime panel, and I've talked a little bit about hemp and lime composites. So it's made of, the panel there is hemp and lime, and it's strapped, we've taken the doors off this environmental chamber. So inside there is an environmental chamber, and then this room space, this rather untidy room space, is environmentally controlled. So at the start of the experiment, we set it up that it was 20 degrees centigrade and 60% humidity on the inside of the wall panel, and exactly the same on the outside as well. And once we'd reached steady state conditions, we changed the temperature on the inside of the panel, and we measured the profile across the panel. So we put a thermal shock across the wall, and we dropped it to 0 or near 0 on the inside of the panel. So basically we had 0 on one side of the panel and 20 degrees and 60% humidity on the outside here. And we wanted to see basically how long it would take to stabilize, because ultimately when it reaches a steady state, you'd expect a linear temperature profile across the wall, and we were interested to see how long it would take. We also did it with mineral wool. So this panel is 300 millimeters thick. To get the same U value or R value with mineral wool insulation, you only needed half the amount of mineral wool, so 150 millimeter wool. So one of the arguments against hemp lime is it isn't as good a thermal insulator, but when we dropped the temperature with the mineral wool, it took 24 hours for that steady state to establish itself. Whereas in the hemp lime panel, how long do you think it might have taken? Less? 3 days, a week. It took 14 days. So this graph represents, so this is the inside, 20 degrees centigrade, and rather than having this in millimeters or centimeters, then it's the normalized thickness. So these are the positions of the sensors, and they were taken at different times, the temperature. And so this goes from 0 to 30 centimeters or 300 millimeters. And so ultimately you'd expect to get a linear profile across there as it reaches a steady state. But even after 48 hours, the temperature is still relatively warm, considering that we've dropped it to 0 or near 0 on that side. So it's really taking its time because of that movement of moisture. It's not just about, so that additional thermal mass or latent heat energy effect of having a hygrothermal material. Now, we haven't done the same experiment on a clay-based wall yet, but I would very much like to do so just to see what the similar effect there. But obviously taking that amount of time is really beneficial to the performance of the material, because obviously we never, as people keep saying, we never reach a steady state in a building. It's a transient dynamic environment, but that additional effects there goes a long way to benefit the thermal performance of that wall and help explain why we think, having U values or R values don't tell us everything by any means. Just a couple of the other aspects of the project related to this. We also looked at sheep's wool. Now, it's well known that sheep's wool as an insulating material will absorb formaldehyde. So this is an experiment to demonstrate that. So this is relative humidity and this is mass. So this is an isotherm, and I showed it in the previous presentation. I'm going to show a few more of these type of curves with clay. And so basically as the humidity goes up from 0, then the equilibrium mass increases, and then as you take the humidity down, it goes back down. So this was with sheep's wool in a chamber, and then the next curve is the chamber, the humidity was increased, but also inside the chamber, formaldehyde was introduced as well. And So when there's just water, then it's an elastic, although there's this hysteresis effect, it doesn't come back down the same curve that it goes up, but it does return to zero. Whereas when the formaldehyde was introduced into the chamber, it doesn't return to zero, and there was a net mass gain in the sheep's wool. So the sheep's wool proteins were absorbing the VOCs, so removing the VOCs from the atmosphere. So a benefit of using sheep's wool in construction. We also developed photocatalytic materials compatible with lime plasters. So photocatalytic coatings, particularly using titanium dioxide, is well known on external surfaces. Here the challenge was using it on internal surfaces where the UV levels are much lower, and also using it on clay and wood panel products. And the idea of titanium dioxide is that the light impinges, sets the electrons, which then react with gases to oxidize them and remove pollutants such as VOCs. We also developed wall panels, prefabricated wall panels using those products, using a combination of sheep's wool, cellulose insulation, clay finishes, and we'll have a look at a bit more. But I'm going to focus on the clay coatings. So the reason why we wanted to use clay coatings and why we worked with Claytech on this project was, of course, they're known for their good absorption and desorption properties. They help contribute to an indoor climate regulation. They're healthier to use for the builders who are actually using them, because that's an aspect of using materials that we often overlook. We think about the health of the end user, but also for installers. If you see people installing some insulation materials, mineral wool or others, or the expanding foam, then they're often covered in breathing masks and personal protection equipment. It's a low energy material. It can be repaired relatively easily. You can replastify, as we've seen some of the work that Joma was talking about. You can re-wet it and repair cracks, and at the end of it you can reuse it. So these are some images just from Claytech. You know, we're using different subsoil materials, different colors, different minerals, and they have a very mechanized processing plant in Western Germany. I think they now employ about 50 people, producing a range of unfired clay products, where clay plasters in particular is one of their major products, which they sell in sort of dry forms, in tubs, in bags, and you mix it on with water and use it. And this is installing it here, and then there's usually in a two-coat surface, so you've got a base coat there and then a finish coat. And he's putting on the top coat and he's floating it off and then producing these amazing finishes. People are attracted to clay plasters because of their health benefits and their environmental impact, but they're also increasingly just simply attracted to them because they look great. So this is absorption. This is going back to the absorption curve here. This is for two clay plasters as produced by Claytech, showing the mass change with humidity going up and then coming back down, and one having the base coat, the top coat having more hygrothermal performance, absorbing more moisture for each humidity stage. It's a bit fuzzy, but this attempts to show that curve and the state of moisture in the material. So in the sort of dry areas, then you've got a single layer of water molecules, and then as more moisture comes in, you've got multiple layers, and then at the higher levels where you got humidity sort of 70, 80, 90, then you've got interconnected layers, capillary condensation, and then really when you get closer or above up to 100%, you're starting to get free water in the pores and then eventually saturation. So in going back to the idea that we want to create an environment where we're between 40 and 60%, then with humidity, then we're very much in that zone there. So one way of measuring a material's capacity to regulate environment is to measure its moisture buffering value. And what you would do in that test is to put the sample in a regime where you cycle the relative humidity over time steps and measure the weight mass change of the sample in response to that. So there are different international recognized tests. There are ISO standard tests which have different ranges of humidity, and I think some have slightly different time steps as well. So you have a chamber where you can program it to do these steps, and what you would do is prepare your specimens here and then put them on scales and record their mass change as you change the humidity inside that chamber. And so you might get a response like this. These are two materials. You would hope to get a response like this. One is one of the clay plasters, and one is gypsum, because gypsum is the major competitor that these plasters are challenging, or it certainly is in UK. And so these are actual relative responses of these two materials. So we see here the typical curve is that once you're at steady state there, then you whack up the humidity, and the material responds by increasing mass in this sort of non-linear response, and then you drop the humidity and it releases it, and then you change humidity again, and you get this sort of sawtooth response, which takes about 4 cycles before it stabilizes and becomes completely sort of elastic, in the sense it's doing the same thing. Whereas with the gypsum, I mean, in the case of the clay, it hasn't flattened off, whereas in the gypsum, the gypsum has absorbed some moisture, but it's pretty quickly, within that time frame of a 12-hour cycle, reached its capacity for moisture absorption. So to compare different materials, you use something called moisture buffering value. So a small amount of maths. So we've got 2 responses for clay and for gypsum, and the moisture buffering value is simply measured as the amount of water absorbed per square meter of the sample. So if we know the area of the specimen here, then, and we know the amount of water it absorbs in a typical cycle as measured by the height between there and there, and then we divide it by the change in humidity, that step there, then we can calculate the moisture buffering value as grams per square meter per relative humidity percentage. And so we've done that both for the clay and the gypsum, and the sort of classification of moisture buffering value has things ranging between negligible, so materials that aren't really moisture buffering, through to materials where you get an excellent response, a simple grading system based on that moisture buffering value. And most clay plaster materials are coming in at this level, and I think the gypsum was coming in at sort of a limited value somewhere there. So how thick is thick enough? And that's a question that I think many of us have been asking in relation to some of our world leaders, as well as clay plasters. But talking about clay plasters, then one of the questions was posed is, well, how much clay plaster do you need to put on a wall for it to be effective? And maybe at what point are you putting on too much, and maybe you can put on less? So we decided to do a series of experiments where we basically made a series of 5 the same material thickness, the same materials at different thicknesses. It was very tricky to make one at just 2 millimeters by itself, and then 4, 10, 20, and up to 40 millimeters. So going back, to this figure, the image here, then we made specimens of 2 millimeters, 4, 8, and so on, and put them through that test. And what we wanted to do, we'll get there in the end, is find out whether what one really is the thickness that we need. We want to make sure that we don't have insufficient capacity, but equally maybe we don't want to have excess capacity. I mean, there may be other reasons why you want a 40 millimeter clay plaster for the substrate or for other uses. It may even have a structural use. But if it's just there for moisture buffering, what's the amount that you need? So they're the different specimens made up there of different thicknesses. And we measured the moisture buffering value. You can see the different response rates. So the 2 millimeters is the solid line. And you can see, like the gypsum earlier, it flatlined pretty quickly. So it had reached its capacity for that humidity step change. And then the 4 millimeters absorbed more moisture, funny enough, about twice as much, but also flatlined. The 10 millimeters wasn't quite the same, and then by the time we got to 20 and 40, they pretty much were the same responses. So then we plotted, and we did it for the top coat and the base coat, and then we plotted the moisture absorption values against thickness. And by some linear regression analysis, we estimate that the thickness that you need is between about 8 and 10 millimeters, about a centimeter of material. For these particular materials, we haven't done it. I'd like to expand this for other clay plasters, and also to play around and look at different humidity regimes as well. But it would seem about a centimetre of clay plaster is enough to give you your moisture buffering that you require. Also in the tests, we looked at thermal conductivity. So we added materials, and this. So looking at the density against thermal conductivity of the clay plasters, then it follows a reasonably, there's clustered around here, but generally speaking, thermal conductivity is fairly linear relationship with density. So the more dense, the better the thermal conductivity, or the less insulating. And so by adding some hemp, we got the thermal conductivity down. But let's face it, when it's only 10 millimeters thick, then the overall contribution it makes to the thermal insulation of a wall panel is relatively negligible. We also looked at different clay plasters with adding hemp shiv to in terms of enhancing its moisture absorption values, and sort of the blue and the pink responses here significantly improve the moisture buffering or absorption values by using hemp because of its pore structure. Hemp is a very hygrothermal material, more so than even clay. We also, because we're interested in VOCs, we did some tests looking at for a variety of materials, mainly the sheep's wool, but we also did some VOC tests on clay plasters. And so you put your specimen in this tube and you introduce the VOC in one end, and then you measure the outlet as well. And if it has diminished, then the specimen has absorbed some of the VOC gases. And so the three gases we particularly looked at were toluene, limonene, and dodecane, which are all volatile organic compounds. I'm not a chemist, but I think limonene is one of that lemony smell that you sometimes get with cleaning products and air fresheners. And so this is the change in concentration of toluene, limonene, and dodecane, passing it through one of the clay plasters. And the clay plaster itself was effective at reducing there was some cellulose and straw material in there, but it was very effective at reducing VOCs as well. So I think evidence that clay plasters can be used also to remove VOCs from the atmosphere. So a further benefit of using clay plasters. We wanted to put these products together to make panel products, prefabricated panel products I mentioned before. And in the development, then we did some work on the studs. So this is a section here. So the timber studs are made from very simple OSB and softwood flanges, but to minimize the thermal bridging and minimize the weight, then we cut holes in them, as you can see here, and we did structural testing on there in compression and in bending to see if they were still sufficient. We've done fire testing here, and we did acoustic testing as well. So this is an acoustic test panel set up there with the sheep's wool insulation. And then we did some comparative demonstration tests. So these are two identical, we did 4 cells, 2 pairs, 2 in, as you have said before, 2 in Spain, 2 in England. One was used the EcoC panel products, including the clay plasters, and one used the major competitor, which was mineral wool insulation and gypsum. And they were both designed to have exactly the same U value or R value. So they have a U value to meet passive house. So they're a U value of 0.15. So about, I think that's an R value of about 7.7. So they're 30 cubic meters of airspace, which is a standard sort of volume size. And so we measured their performance over a year. We also did air tightness testing and VOC testing as well. And then we also, in Spain, in Seville, this is in Madrid, this is in Seville, looked at performance of an EcoC panel against a standard masonry wall panel, which was used in Seville. And then this is another EcoC panel. They're all clad with OSB because the system is set up that you can put a variety of different cladding systems, whether wet, rendered, or dry lined. So we weren't too bothered about particularly what went on the outside as long as it was the same. And then we also did some demonstration with the clay plasters on the inside of different buildings as well. So this is the construction of one of the EcoC cells. So it's got the sheets wool insulation and then a liner board, and then, as you can see, Claytech plastering, putting the base coat, which is one of the ones we introduced the hemp shiv into as well. We also did panel testing in our large environmental chamber, which is this thing here. So we've got two environmental chambers, and we can stick a wall panels in between and play around with the environment on one side and compare it against the other, and then measure the heat flux and measure the temperature and conditions through the panel to compare the performance. And that one is with a clay plaster on. I think this is gypsum plaster. And there's another test as well, a slightly different view. And there's the chamber. And then we also did acoustic testing on the panels, on the pods as well. And basically, some of the results that we got from comparing the gypsum with the clay in those tests was all, thankfully, all good. So the humidity control in that 30 cubic meters was improved by using clay. The CO2 levels were lower. The particulate matter was lower. The VOCs in particular, the formaldehyde was all lower. So that was all a good news story for using clay plasters as opposed to gypsum plasters. Energy efficient wise, they're about the same, but they were designed to be the same. So there wasn't a performance gap particularly. They both came out as about what they were designed to do. So overall, coming to the end, some of the project outcomes, we got an improvement in the thermal resistance of the clay plasters. We got improvement in the moisture buffering of the clay plasters. We got a significant improvement in the VOC capture potential of sheep's wool. We improvised with that. And we got, in comparison to the EcoC test site with the standard timber frame and masonry construction, there was a 50% reduction in energy performance for using the EcoC panels as well. This is the last slide, which the only relationship between EcoC and this photograph is that Claytech did this. This is the Apple store in Brussels. There's a similar one in London, if you ever visit either Brussels or London. And these these walls here are lined with clay plasters, and these were designed by Norman Foster practice. And they chose clay plasters not because of their hygrothermal performance, or even, I think, because of their favourable environmental product, but they did it because they liked the look of them. And Apple, that's a company that's seen at the forefront of innovation and leading the world in all things IT, and they're choosing, they're seeing clay material as a material that's compatible with the image that they're trying to create as Apple as a moving forward. So that's a very powerful image. So as I say, if you're in Brussels, then you can go and have a look there. But if you're in London, then in Selfridges on Oxford Street, on the ground floor, they've got an Apple store there. They don't like you taking photographs, I've learnt, but you can go and have a look and maybe get a quick photo if you're pretending to look at your texts. Checking your new iPhone. If you want to check out more, there's a video about the project as well at the website. And yeah, that was the EcoC project. So thank you very much for your attention.